Next, we consider Nilradical and Jacobson radical of a ring. So we start with this proposition. So there is a ring A in which we consider the set R of all nilpotent elements, and the claim is that it's an ideal. The set of all nilpotent elements is itself an ideal of A. And after proving this, if you then form the quotient of A by R, you get this quotient ring that has no non-zero nilpotent element. So let us first show that R is an ideal of A. We have to start, of course, by noting that R is non-empty. That is needed first. Since 0 is always in R. Why though? Because 0 is a nilpotent element, the first power of 0. 0 to the power 1 is 0 itself. So by definition, it's the nilpotent element. So it's there in R. So R is a non-empty subset of A. Now, gradually, we just go for the conditions for an ideal. Let X and Y be two elements in R. That means they are nilpotent elements. Then some mth power of X equals 0 and some nth power of Y equals 0 for some positive integers m and n. So this comes straight from the definition of nilpotent element. Okay, now what can we immediately say from this, from these two equations? Then the first easy thing we get is this. Let us consider the mth power of the additive inverse of x, minus x. Okay. So you know that in any ring which has an identity element, and our rings always have identity elements, minus x can be written like this. On top of that, we are in a commutative ring. That is why you can write like this. Okay. Now x to the power m is 0, so it's going to be 0 ultimately. Which in a ring is 0. That means just like x, a power of minus x is 0, where the exponent is a positive integer. And we are simultaneously going to say something else. And for any element A, in A, we also have this in a similar manner. This step again uses the commutativity of our ring. Okay, so these two things tell us what? Namely that minus x and ax are both nilpotent elements. So minus x and ax both belong to R. That alone, of course, is not enough to say that R is an ideal. We still need to show that the sum of x and y is again a nilpotent element. So next we are going to go for that. Now, by the binomial theorem, which is true in any commutative ring, let us expand this expression, this power, and I am going to write the actual sum for the binomial sum. That's not exactly how you find it in the book, but I am going to write that anyway because that I find is easier to understand. So this will equal this summation. You first write the binomial coefficient. Let me write k, say, as the index of this sum. K varies from 0 to m plus n minus 1, and we have x to the power k times y to the power m plus n minus 1 minus k. Alright, fine, no problem with this. Now, what can we say from this expansion? Suppose some index k, so you actually have to say what happens to each term of this sum. That means depending on k, the terms will change. Say, let us concentrate on those values of k which are greater than or equal to m. Okay. If k is greater than or equal to m, then what can be said about this power of x by one of the rules of exponents? You can write it like this. See, you have to be a little careful in applying these rules of exponents. You cannot just blindly apply them as if you are in a group. The ring is not a group with respect to multiplication. Even when it is a field, the entire ring is not a group with respect to multiplication. However, still you can apply this rule of exponent provided the exponents are non-negative integers. That is why, and in this case we can do that because k minus m is non-negative and m already is positive. Okay, so it works here. So we see that those terms in this sum where k is at least m, they vanish actually. They are equal to 0, each one of them. So let us now concentrate on the other terms. Let us concentrate on those cases which are non-negative but they are less than m. Then m minus k is positive, and so if you add n minus 1 to both sides of this inequality, what will you get? N minus 1 is less than m plus n minus 1 minus k, or because we are dealing with integers, this is an integer and this is also an integer. If you add 1 to this smaller integer, it will still be less than or equal to that larger integer. Okay. In other words, n will be less than or equal to this m plus n minus 1 minus k. So you see that those terms in this sum where k is less than m, for them however, this m plus n minus 1 minus k is greater than or equal to n. So for this type of terms, that power of y will vanish. because now you can apply your rule of exponent here. I think it's better to write like this. Y to the power n plus, well, we are already going to subtract n from this. Times y to the power n. This inequality ensures that this is a non-negative exponent, and that is why you are able to use this rule of exponent here. Or minus n we have to write. 0, because y to the power n is 0. So this is 0. So the remaining terms also vanish. Everything vanishes. Hence, this is equal to 0. Now before you conclude that this shows that x plus y is a nilpotent element, there is one more thing you need to verify. Verify means at least see. Is this a positive integer? Yes. Why? Because the smallest values that m and n can take are both equal to 1. Even in that case, this is equal to 1. Okay, it doesn't become 0 or negative. That is why this really is a positive integer. Since, in fact, you should mention that is a positive integer. So now we can conclude that yes, x plus y is also nilpotent. Now we have all the pieces to claim that R is an ideal. Thus, R is an ideal. So we have proved one half of the proposition. Now we go for the other half, namely that the quotient ring of R by this, of A by this ideal R does not have a non-zero nilpotent element. So for the second half, so how does an element in the quotient ring A slash R look? It's a coset of the ideal R. So it will look like this. B nilpotent, where of course it's understood that X is an element of A. Now this being a nilpotent element in this ring means what? Some positive integral power will be equal to 0. 0 of that ring, which is R. Then X plus R to the power, what shall I take? You can actually take M again, but because we are in the same proof, let me take I. Okay, this is equal to the 0 element of the ring for some positive integer I. Now you can work on this equation and get something. First of all, you get this, because if you apply the definition of multiplication in this ring, this ith power will be equal to this coset. Keep in mind, I is a positive integer. Okay. That in turn implies what? It implies that the representative of this coset, x to the power I, that element has to belong to R itself. However, what does this mean? This means that x to the power I is a nilpotent element in the original ring A. So if I continue like this, then I can write this. So some power of x to the power I will be equal to 0 for some positive integer j. And what does that imply? Keeping in mind that I and j are both positive integers, there is that other rule of exponent as well, which you can use. That is x to the power ij. However, note that ij is also a positive integer. So this makes the element x itself a nilpotent element. That means x belongs to R. But if x belongs to R, then the quotient x plus R has to be equal to R. So what have we shown? We have shown that if you take a nilpotent element in A slash R, that is nothing but the zero element. And that is why we said that this ring has no non-zero nilpotent element. Zero, of course, is always a nilpotent element, but besides that, there is nothing else. So that is the proof. Now, this R has a name. The ideal of all nilpotent elements is called the Nilradical of the ring. We call R the Nilradical. This is one word, okay. Nilradical of the ring A. Okay, so the Nilradical is the ideal consisting of all the nilpotent elements in the ring. Now there is a characterization of this ideal in terms of the prime ideals of the ring. It turns out that this ideal is actually equal to the intersection of all the prime ideals. See how strange and nice this is. Prime ideals intersect to give you the set of all nilpotent elements, which is this next proposition. With R having the same meaning here. Okay, so I am going to use R and A everything from our existing discussion. R equals the intersection of all the prime ideals of A. Let's now prove this. Let us first give the collection of all prime ideals of A some name, because that way you can see the things, okay? You won't get confused. Let P be the collection or set of all prime ideals of A. And we are interested in the intersection of the elements of this collection. So let us call this R prime. Let R prime be the intersection of all the ideals in P. So R prime is the intersection of all the prime ideals of A. Our aim now is to show that R prime is equal to R. Okay, so how shall we show this? The way the proof proceeded in the book is this, of course. One half of this, that is showing that R is a subset of R prime, is quite easy. So let f be an element in R. What does that mean? It means that f is a nilpotent element in our ring. Then, so some power of f, say f to the power n, will be equal to 0 for some positive integer n. It's a little cumbersome to keep writing for some positive integer. I forgot if the author is using some special symbol to denote the set of positive integers. If not, I mean, I don't remember exactly. I only remember that he uses the ordinary this z to denote the set of integers. But I am henceforth going to write the set of positive integers like this. Okay, so that will reduce the labor of writing many things. Alright. So, for any prime ideal is okay, yeah, this is the advantage. Why am I writing again? So far, this is the advantage of writing only some things in the beginning. Any I belonging to P. This means that I is a prime ideal of A. This belongs to I because I being an ideal obviously has the 0 element. So you see that the nth power of the element f belongs to I. Now you use the fact that I is a prime ideal. Since I is prime, so f itself has to belong to I. I mean the actual definition that whenever the product of two elements belongs to a prime ideal, at least one of them has to belong to it. If you apply that definition to f square, say, then it tells you that f has to belong to I. But you can keep on using this property, or in fact the definition of prime ideal, to any higher power of f. If say f cube belongs to I, then f cube is f square times f. So either f belongs to I or f square belongs to I. If f belongs to I, fine. If f square belongs to I, then again you get that f belongs to I. So that's why in any case f has to belong to I. Okay. So what are we getting then? We are getting the fact that f belongs to every element of P, every prime ideal. Hence, f belongs to R prime, their intersection. Thus, we have proved that R is contained in R prime. Now we are going to prove the converse, that R prime is contained in R. Okay, but we will do it in an indirect way. And the indirect way is this. So what we are going to do, next we are going to consider an element f, not that same element, some element f which is not in R. Okay. Conversely, let f be not in R. Now, f being not in R means what? It means that f is not a nilpotent element. Yeah, f is not a nilpotent element. And now next what the authors do, consider the following collection of ideals, and they are calling it sigma. You can guess where this is all going. We are going to show that this sigma is partially ordered and on it Zorn's lemma can be applied. What are the elements of sigma? The elements of sigma are ideals. I is an ideal of A such that this f to the power n does not belong to I for all positive integers n. But according to what I said just now, I can write that compactly like this. So what are the elements in this sigma? In this sigma, the elements are the ideals of A, not all ideals, but those ideals that do not contain any positive integral power of f. For every n belonging to z plus, this f to the power n is not in I. That type of ideals I have been collected and their collection is sigma. Okay. Now obviously sigma is partially ordered by set inclusion. Clearly, this is a partially ordered set, and the authors then directly write, and I am also going to directly write, by Zorn's lemma. But by now you know very well that you cannot just simply apply Zorn's lemma to any partially ordered set. You need to show that every chain in it has an upper bound, and that part I am leaving to you. In this partially ordered set also you show that every chain has an upper bound. With the experience that you have with this type of things, you have seen it twice already, you should be able to do this. Okay, so that part is left to you. I am straight away applying Zorn's lemma. Sigma has a maximal element. Let's call it P. Okay. Sigma has a maximal element P. So being an element of sigma, what is P? P is also an ideal satisfying this property. Now let us show that P actually is a prime ideal. Okay, let us next show that. That however you won't get directly from this alone. We have to separately show that. We now claim that P is a prime ideal. Okay. That however requires P to first of all be a proper ideal. Is P a proper ideal? If not, then of course P is equal to A. But is that possible? No. Why? Because you see, the element F is after all an element of A, because everything is happening inside the ring A, right? So F is equal to F to the power 1. That however is equal to, that is in A. So P cannot possibly be equal to A, because P has to satisfy this not just for n equal to 1 but for all positive integers n. And that is why you write, since F equal to, or F to the power 1 equal to F belongs to A, P is not equal to A. So yes, it's actually a proper ideal. Next, we have to prove that if the product of two elements in A belongs to P, then at least one of them belongs to P. But here also, we will prove the contrapositive. Suppose X and Y be two elements in A such that X, Y, well, yeah, this part is really very confusing. I am also getting confused. What does primality require? Primality requires this. X belongs to P or Y belongs to P. What is its contrapositive? Negation of this, that is, X does not belong to P and, because I am taking negation, now becomes and, Y does not belong to P implies XY does not belong to P. So if instead of showing this, if I show this, then also it's the same as showing that, because an implication and its contrapositive are logically equivalent. And this is what we are going to show. So okay, yeah, this is how we have to choose X and Y, not just simply elements of A, but elements of A which are not in P. That means neither X is in P nor Y is in P. Yeah, and now I have to show that XY is also not in P. But how do I do that? Well, this is how. Then the ideals P plus X and P plus Y both contain P properly. What does this mean? You see, we already know that when we take the sum of two ideals, it's also an ideal. In fact, we have already discussed about this. It's actually nothing but that ideal generated by the ideal P and the element X. It turns out that that is equal to this sum. But anyway, it's an ideal. And obviously, it contains P as a subset. But why does it contain P properly? Why is P a proper subset of this? Well, because besides containing P, this ideal also contains the element X, which is not in P. So this cannot possibly be equal to P because it has an extra element X, at least one. And that is why it properly contains P. Just like that, this one also properly contains P. However, P is a maximal element of that collection sigma. So can these ideals belong to sigma? No, because if they are in sigma, they would violate the maximality of P. Hence, and are not in sigma. Okay. But what are the properties of the elements of sigma? Well, I mean, there is only one property, which is the definition of sigma. It says that any ideal which is an element of sigma does not contain any power of f, any positive integral power of f. This ideal, for example, is not in sigma, which means that it must contain at least one positive integral power of f. Similarly, that one. But then some f to the power m has to belong to P plus X and similarly some possibly different integral power of f belongs to p plus y. For some positive integers m and n. Okay. You may have noticed that here I got a little confused, but I cleared that confusion up by writing that what the implication is, what its contrapositive is. This is how things should go. It's not that you have to remember everything by heart. Wherever you get stuck a little, you should be able to find your path, unless you have forgotten actually everything. Okay. Now, what does this mean? This means that f to the power m is some element of p, let me call it pi 1, okay, or if pi looks weird, let me call it p1, plus some element from here, which is it will be a multiple of x, alpha x, and this is the p2 plus beta x for some p1 and p2 in P and alpha and beta in A. Well, I think I made a little mistake in the notation. In the beginning itself, I can see what mistake I have made. It's not exactly a mistake, but it is also a mistake in a sense. P already represents the collection of all primordials. Here, however, I have used P to denote a maximal element in sigma. Okay, so that actually I cannot do. So let me change this to Q. In the book you will see P because they haven't really given any name or in fact even considered the collection of primordials. They straight away talked about the intersection. Q, this is also Q. If you want, you can change these also. Q1, Q2. Belonging to Q. Yeah, now it's okay. Thus, what will happen if we now calculate this? This of course will be the product of these two expressions, these two elements. One more thing, where we declared that a maximal element in sigma exists, there I must have written P, change that to Q. So now this is Q1 plus alpha x times Q2 plus beta y. Now if you do the multiplication, you get Q1 Q2 plus Q1 beta y plus Q2 alpha x plus alpha beta xy. Alright. Now notice that Q1 and Q2 are elements of this ideal Q. So obviously Q1, Q2 is again in Q, and so are Q1 beta y and Q2 alpha x. because capital Q is an ideal. So you multiply the ideal element Q1 by any ring element beta y, it's again in Q. Similarly that one. So this part is an element in Q. However, this part is a multiple of x, y, and that is why this entire thing belongs to Q plus xy. Now, what was m and n? What were m and n? M and n were positive integers, so their sum is also a positive integer. So you see that this is an ideal of our ring which contains a positive integral power of f, which means that this cannot be in sigma, okay, because the elements of sigma are like that. So this cannot be in sigma. Yes. It does not belong to sigma. And that is why x, y cannot belong to Q. Why? Because if xy belongs to Q, then this principal ideal generated by xy will be a subset of Q, and so the sum of Q and that will actually be equal to Q. Q, however, is in sigma, so that is why this cannot be in Q. But that's what we wanted to show, right? In other words, we have shown that x not in Q and y not in Q implies that xy is also not in Q. Hence, Q is a prime ideal. Alright. Now, let us again go back to the fact that Q is actually an element of sigma. So, no positive integral power of the element small f belongs to Q. In particular, f itself does not belong to Q. So, how did we start this part of the proof? In this part of the proof, we chose f to be an element which is not in R. Yeah. That means f is not a nilpotent element. Yeah, that's how we started the proof. I mean, this half of the proof. F is not a nilpotent element, and then we showed that f does not belong to a prime ideal, which means what? That f cannot belong to the intersection of all prime ideals, which is our R prime. That is, if f is not in R, then f is not in R prime. What does this mean actually? I mean, if you translate it into sets and operations without using elements, this is what it means. the complement of R in A is a subset of the complement of R prime in A, which in turn implies that R prime is a subset of R. Now you combine this containment with the previous one, which was R is a subset of R prime, that finally gives you that R is equal to R prime. R is the set of all nilpotent elements, R prime is the intersection of all prime ideals. So that's how you have this result. And this result motivates us to do something similar with maximal ideals. That is, just like we have considered R prime, we can also consider the intersection of all maximal ideals. If we do so, we obviously again get an ideal, because intersection of any collection of ideals is an ideal, and that ideal is called the Jacobson radical. The intersection of all the maximal ideals of A is called the Jacobson radical of A. And finally, let us see this result which characterizes the Jacobson radical. This is proposition 19. Well, for some reason the authors have decided to call this Jacobson radical also capital R. Let me, however, give it some other name. Let me call it J. Okay, J for Jacobson. So this is a characterization of the elements of J. X is an element in the Jacobson radical if and only if 1 minus xy is a unit in A for all elements y in A. Okay, an element of A, x, will be in the Jacobson radical if and only if the elements 1 minus xy are all units and y is any element of the ring A. That is a very stringent condition. So how can we substantiate this? Here also the proof is quite twisted. I mean, both the halves have been proved indirectly. Okay, not directly. You understand in what sense I use that word. So this is how the proof starts. Let 1 minus xy be not a unit for some y in A. Now you recall a previous result which tells us that every non-unit is contained in a maximal ideal. We got this result as one corollary to existence of maximal ideals, that thing, and it is corollary 1.5 by corollary 1.5 1 minus xy belongs to M for some maximal ideal M of A. Alright. Now what does that mean? It means that, well, it obviously means what it means. Now the question is this: can x belong to J? We want to show that x is not in J. But why? Because that's how we have started. We are assuming that 1 minus xy is not a unit. So we want to say that x is not in J. However, suppose, contrary to that, suppose x belongs to J. Now what is J? J is the intersection of all the maximal ideals. So x will be in every maximal ideal. In particular, x will belong to M as well. And so x, y will also belong to M. But then you have this element in M and that one in M, so their sum is also in M, which is 1. Which is not possible. Why? Because M is maximal and so must be a proper ideal. However, if M has 1, M has to be equal to the ring. It cannot be a proper ideal. That is why. So this supposition must be wrong. Thus, the supposition is wrong. Let me not write those things. So x cannot belong to J. So what have we shown? We have shown that if 1 minus xy is not a unit for some y in A, then x is not in J. The contrapositive of this is that if x is in J, then 1 minus xy must be a unit for every y. That's what we have shown. Now we go for the converse. Conversely also, here also we go indirectly. Conversely, let x be not in J. Okay, so then what do we get? Then x must be not in at least one maximal ideal. Then x does not belong to M for some maximal ideal M of A. All right. Okay. Hence, the ideal generated by M and X will contain M properly. And combine with that the maximality of M, and you get the fact that this ideal generated by M and X has to be equal to the entire ring. This thing. But as we saw there, this is actually nothing but the sum of M and the principal ideal generated by X. But anyway, you can use this also. Must equal A. So 1 belongs to this ideal. Thus 1 is equal to some element from M plus xy for some M in M and y in A. This implies 1 minus xy, which is M, it belongs to M. So 1 minus xy is an element in this maximal ideal, so it cannot be a unit, because otherwise again M has to be equal to A, which is not true. Thus 1 minus xy is not a unit. In other words, if x, now what we have proved, if x is not in J, then 1 minus xy is not a unit for some y, right? In other words, if 1 minus xy is a unit for every y, then x has to be in J. So this way we have the proof as well of this fact. So let me just end the video here itself. Tomorrow we have, I don't know if you have noticed it or not, I have decided to upload 2 videos, okay, on one day if we have them in the schedule. So tomorrow we have calculus as well as class 11 physics. So I will do both of them. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Brain. Have a nice day.